Here's the strange part. Every astronomer arguing about K2-18b is looking at the exact same numbers. Same telescope, same light curve, same wiggles in the spectrum. No new data. No secret data set one side has and the other doesn't. And yet you can find serious, credentialed scientists calling this planet a promising ocean world with a chance of life, and other equally serious scientists calling that conclusion close to meaningless. This isn't a fight about facts. It's a fight about what the facts mean. And it's one of the clearest windows we have into how messy science actually looks while it's happening, instead of after it's been cleaned up for a textbook. K2-18b is a planet about 120 light-years away, roughly 8.5 times the mass of Earth, orbiting a red dwarf star in a zone where liquid water could theoretically exist on a rocky surface, if it had one. It's bigger than Earth, but smaller than Neptune, which puts it in a size category we don't have a single example of in our own solar system. That matters more than it sounds like it should, because it means we're guessing at what kind of planet this even is, based on models built from extrapolation rather than direct comparison. In 2023, the James Webb Space Telescope looked at K2-18b as it passed in front of its star and captured starlight filtering through the planet's atmosphere. Different molecules absorb light at different wavelengths, so the resulting spectrum works like a fingerprint. Astronomers led by Niku Madhusudan at Cambridge reported methane and carbon dioxide, and, more provocatively, hints of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by living organisms, mostly marine phytoplankton. That single word, hints, is doing enormous work in this story. The 2023 detection of dimethyl sulfide, DMS for short, was weak. Then in 2025, the same team announced a stronger follow-up detection, describing it as reaching a significance of around 3 sigma. If you're not used to statistics, 3 sigma sounds impressive. It's not nothing. But in physics, the standard for calling something a discovery is usually 5 sigma, which represents roughly a 1 in a few million chance of being a random fluke. 3 sigma is closer to 1 in a few hundred. Historically, in physics and astronomy, a huge number of 3 sigma results have evaporated once more data came in. So already, before anyone accuses anyone of bad science, there's a built-in fragility here. The claim rests on a statistical signal sitting exactly in the danger zone, strong enough to write a headline, not strong enough to end a debate. That's the first reason identical data produces different reactions. One group looks at 3 sigma and sees the beginning of something enormous. Another group looks at the same 3 sigma and sees a coin that's landed heads a few extra times in a row. But the disagreement goes much deeper than a single statistical threshold. And this is where it gets genuinely interesting. Several independent teams reanalyzed the very same Webb data using different modeling approaches, and some of them didn't find convincing evidence for dimethyl sulfide at all. Not because they had worse data, because spectral fitting is not like reading a barcode. It's closer to looking at a blurry, noisy signal and asking which combination of molecules, at which temperatures and concentrations, could have produced it. Multiple different combinations can produce nearly identical-looking spectra. Astronomers call this degeneracy, and it means the best fit model depends heavily on which molecules you decided to test for in the first place, and which reference data, called cross-sections, you use to represent how those molecules absorb light. Critics, including researchers like Ryan McDonald and others working independently, pointed out that some early DMS claims used cross-section data that could be confused with a completely different, far more mundane molecule. If you swap in updated reference spectra, the supposed biosignature signal weakens or shifts towards something else entirely, something with no biological implications at all. This is the equivalent of finding a fingerprint at a crime scene and then discovering the reference fingerprint database you used to identify the suspect was mislabeled. The print on the glass didn't change. The interpretation of whose print it is did. Then there's a second, arguably bigger fight, which isn't about the molecule at all, it's about the planet itself. Madhusudan's team has argued K2-18b could be a Hycean world, a term they coined for a theoretical class of planets with hydrogen-rich atmospheres sitting over global oceans of liquid water, potentially warm and habitable, like a planet-sized version of Earth's oceans. It's an elegant idea, and it's the reason the DMS detection got so much attention. Ocean plus atmosphere plus a possible biosignature molecule sounds like the setup for a real answer to whether we're alone. But other researchers, using the same mass and radius measurements, modeled K2-18b completely differently. Some argue that at K2-18b's size and internal pressure, you likely don't get a nice temperate ocean at all. Instead, you get pressures so extreme that any water layer would exist as a strange high-pressure ice or a supercritical fluid, not a familiar ocean, sitting on top of a rocky or even a magma-covered interior heated by relentless pressure from above. In some of these models, the surface, if you can even call it that, would be far too hot and crushed for any Earth-like chemistry, let alone biology. Same mass, same radius, same orbital distance from the star. Completely different planet, depending on which internal structure model you trust, because we cannot directly observe what's happening under that atmosphere. We're inferring it entirely from indirect physics, so now you have two separate layers of uncertainty stacked on top of each other. Layer 1. Is the DMS signal statistically real, or an artifact of noisy data and incomplete reference spectra? Layer 2. Even if a sulfur-bearing molecule really is there, does this planet's interior even permit the kind of ocean where biology, as we understand it, could exist? You can disagree at either layer and land in a completely different camp, using the exact same transit spectrum as your starting point. There's a third ingredient that rarely makes it into headlines but matters just as much: instrument systematics. Webb is an extraordinarily sensitive telescope, but that sensitivity comes with new kinds of noise nobody had to deal with before at this precision. Detector effects, pointing jitter, and subtle calibration drift can all imprint tiny wiggles onto a spectrum that look, to an eager eye, like molecular absorption features. Extracting a clean planetary signal from raw Webb data involves dozens of processing choices, and different teams make different choices. This is why some of the same raw Webb observations of K2-18b, reduced independently by different groups, come out looking meaningfully different from each other before anyone even starts asking what molecule might be present. Put all of this together, and you get something that looks less like a scientific dispute and more like a Rorschach test with numbers attached. Researchers who already suspected Hycean worlds are common and biosignatures are findable within this decade tend to read the ambiguous data as tentatively supportive. Researchers who are skeptical of the Hycean concept, or who think DMS specifically is a poor biosignature choice, because it can also form through non-biological chemistry, including in comet material and some lab experiments with no life involved, tend to read the exact same ambiguous data as unconvincing. Neither side is being dishonest. They're both doing legitimate science. They just started from different priors, and the data wasn't clean enough to force a single answer. This is actually a really important point about how science works in real time, as opposed to how it gets remembered afterward. We tend to picture discoveries as a clean moment. Someone looks through a telescope, sees the thing, announces it, and everyone agrees. In practice, especially at the frontier of exoplanet atmospheres, the evidence usually arrives blurry, gets fought over for years, and only becomes settled once dramatically better data forces a convergence. That process is happening right now, live, with K2-18b as the test case, and it's happening in public, with press releases before peer-review debates finish, which understandably makes it feel chaotic and even mildly untrustworthy to people watching from outside. It isn't untrustworthy, it's just visible. Most of science's contentious middle phase doesn't usually get broadcast to millions of people